in all the upcoming chapters, almost all the upcoming chapters. So be very particular about. Now what is speed? There is a car and there is an aeroplane. Both are traveling for the same time. The car also travels for 2 hours, aeroplane will also travel for 2 hours. You would say then, but aeroplane will travel a greater distance. What acceleration is, or what do you mean by the situation anything is accelerating? Acceleration is change in velocity over time taken. Why do we say so? Hello students, in today's video we are going to discuss the equations of motion. Now what are equations of motion? It is clear, very clear, that equations of motion are going to be the equations that are going to relate the basic parameters of motion. Do you remember the basic parameters of motion? They were S, U, V, A and T. So if you remember one by one, S here means displacement, U is the initial velocity, V is the final velocity, A is the acceleration and T is of course time. Now before we actually know what these equations are, I want to make it very clear that we can use these equations only when you have a case of uniform acceleration. You have a case of uniform acceleration. So these equations are only valid for the case of uniform acceleration. So keep that in mind. Secondly, these are only giving you an alternate approach to do the problems. So sometimes it becomes very easy solving a numerical using these equations. So I think there is no harm if you know them. Alright. So what are these equations? One by one we will talk about them. Let's start with an example or with a situation. You can see a cyclist at t is equals to 0, it has a velocity u. Now what do you mean by t equals to 0? It is the beginning of time? No. T is equals to 0 in physics would always mean when the observation starts. When the observation starts. So the cyclist might be traveling even before this, but you observed the cyclist for the first time at t is equals to 0. So that is how you interpret t is equals to 0 situation. So since it was moving in the past as well, that is why it already can have some velocity. That is what we call as initial velocity. Now when it is accelerating, its velocity changes to v, let's say after time t. So I hope the situation is clear to all now. T is equals to 0, we start. The initial velocity at that point is u. The final velocity becomes v after a time t. And of course, during this time, whatever is the displacement, we denote it by s. So what are these equations now? These are going to relate s, u, v, a and t, but not all at one time. One by one we shall start. So the first equation, obviously you can see this is v is equals to u plus at. It is relating the final velocity, initial velocity, acceleration and time. And you've already you have the background for this. Why? Because you do understand that acceleration was delta v over delta t, that is change in velocity divided by the change in time. Now what do you mean by change in velocity? If you remember, it is going to be v minus u and the time we denoted by t. So it is nothing but rearrangement of the parameters. You can now see it is at is equals to v minus u, or you may write v is equals to u plus at. So this equation is basically giving you the final velocity after time t in terms of initial velocity, that constant acceleration and time. Again and again I am reminding you, you cannot apply these equations straight away. There is a condition attached, and why it is like that, I will talk about that also. So again, the first equation is v is equals to u plus at. It is not relating displacement. So this equation you can say this is the velocity equation basically, because here we are only relating the velocities. Now when this cyclist is accelerating and it is achieving a velocity v after time t, it has also gone through a displacement s. Now if you remember the formula, the expression for average velocity was change in displacement divided by change in time. Now the problem here is obviously the velocity is changing, but since it is uniformly changing, we can take the average as initial velocity plus final velocity over 2. What is the average velocity? Initial velocity plus final velocity over 2. That means the mean of the first value and the last value. You can represent the average like that, but only if the acceleration is uniform. So this is not always true. This is only true if acceleration is uniform. Now, what is the displacement? S, and let's say what is the time? T. So you can write S is equals to U plus V over 2 into T. This is also a very important expression. The displacement is initial velocity plus final velocity divided by 2. That is the average velocity multiplied by time. Obviously, we have talked about it. Since average velocity is displacement upon time, displacement is going to be average velocity into time. Now, can you use the first equation again here? Of course you can, and replace the final velocity by u plus at. So what have I done here? I have replaced v using the first equation by u plus at. So if I may rewrite this, this will look like what? Ut plus half at square. So now not only you know this equation, you also know the background of it, that how are we getting this equation. So now let's talk about what is this equation. This equation is giving you the displacement. So the first equation where the displacement was not involved, this is going to give you the displacement after time t. Many times you have to do this prediction, that how much will an object travel in this particular time. So I think the second equation can definitely rescue you from that situation. You can easily do that problem. Okay, so again revising, first equation is relating final velocity with initial velocity. Second equation is giving you displacement after a time t. Now sometimes you might also have problems where time is not involved. So the third equation is very different from the first two. Why? Because there is no involvement of time. No involvement of time. So the third equation will tackle such problems where we have to answer what is the displacement in the during which the velocity reaches this value. So you're given the final velocity and you have to talk about the displacement or predict the displacement, and time is not involved. So you can easily understand how do we get this equation. How? So just now we have talked about that S is equals to average velocity, that is u plus v over 2 into t, right? So the displacement is this. Now if I rewrite time, if you look here, I change the color. So if you look here, time from this equation can be written as v minus u over a. So if I use this time and substitute it here, so S will become u plus v over 2 multiplied by v minus u over a. So what is this doing? This is now eliminating time. So we have eliminated time now by putting the value of time as v minus u over a. Can you all understand that? So this is v plus u over 2 into v minus u over a. So now you can rewrite this as 2as is equals to v square minus u square. So sometimes you might see this equation being written as this also, v square minus u square over 2s. This is another way of expressing acceleration. Okay, but for now we are rewriting this as v square is equals to u square plus 2as. But when are we going to use this equation? When time is not involved. When time is not involved. So again, first equation, second equation, third equation, they have relevance. Many numerical you will be easily able to do that. So do keep them in mind. It's not very difficult to know. So v is equals to u plus at, s is equals to ut plus half at square, and v square is equals to u square plus 2as. Okay, we'll take one example of each to understand how these equations will function, but I will give you 1 minute. You can pause the video and you can still write them down if you want to, but at least understand how did we obtain these equations for your confidence to do the numericals. All right. So now, okay, let's take one example. What is the first example? An object starts with a speed of 10 meter per second, accelerates uniformly. So we have to look for this word in the numerical. If they are using the word uniform acceleration or a single value of acceleration like this too, then we can use the equation of motion. Then find its speed at the end of 4 seconds. Looks simple. We are now doing this not by any other means, by using the conventional definition of acceleration, but right now we are interested in using the first equation to solve this. So v is equals to u plus at. Now v is what we have to find out. We just have to plug in the values. The data is given. You can easily relate. An object starts with a speed, so u I am straight away substituting 10. Now what is a? A is 2 and t is 4, because at the end of 4 seconds we have to predict the velocity. Very clear. The answer is turning out to be 18 meter per second. Looks very simple. So it might be a part of a problem, so you should be knowing it. You can't it might not be a complete problem, but a part of a problem you can solve using the equation of motion. Okay, second equation and therefore second example. What is the second example? An object is dropped. Now again, in the previous classes we have talked about it. Whenever the word dropped is used, you would like to believe that it is from the state of rest, and they have clearly written this as well, that dropped from rest. Then find the height through which it will fall in the next 2 seconds. Okay, so they've not given the acceleration, so we would like to believe that it's gravity on the earth which is pulling it down. So we'll take the value of gravity as 9.8 meter per second square if nothing is specified. Again reminding you, we have to look at the introduction of the paper. Sometimes the value of g can be given as 10, then we would have taken it as 10, which is the approximate value. But right now we will take it as 9.8 and start doing the problem. So s, how do you know that we are using the second equation? Because we have to calculate the height of through which it will fall. So basically the displacement. Now u is 0 times t, which is 2 seconds, plus half. I'm just plugging in the values, nothing that I have to do. That's the only thing I have to do. So 2 squared. So what is the displacement that I'm getting? So this is going to be 9.8 times 2, which is 19.6 meter. So by what distance will the ball fall? The answer is going to be 19.6 meter. Easy, very simple. The third equation, which is v square is equals to u square plus 2as, again reminding, will not involve time. So what is the situation? A car is moving initially with a speed of 20 meter per second. All right, so we'll write that initial velocity is 20 meter per second, is brought to rest. So now in fact final velocity is 0. So can you imagine, 20 has become 0. It is a case of deceleration. By applying brakes that provide, oh, they have written it, uniform deceleration of 2 meter per second square. Since deceleration is 2, we will now put the value of acceleration as -2, because deceleration means negative acceleration. Then find the stopping distance. The stopping distance means what distance the car has traveled before coming to halt. So there is no involvement of time clearly. We should rather use third equation where time is not involved, though you can use the combination of first two also to solve this problem. But if you know the third equation, you can get to the answer really quick. So v is 0, u is 20, a is going to be a -2, and s is what we have to find out. So s turns out to be 400 divided by 4, that is 100 meters. So how much has the car traveled before coming to a halt? So the answer is going to be 100. Looks very simple. You should know these equations. I don't see any problem here. And in the next classes, then we will find out how to use these problems in the previous year questions. So we'll do those previous year questions, and then we will feel the importance of these equations. But that's all for this class. I hope you were able to learn with us. Thank you. If you enjoyed this video, please don't forget to like, share and subscribe to our channel.